Hi guys, this video is going to take a look at the theoretical aspect of the Biot Savart and the Ampere's laws, which in class and in the laboratory you can collect data and come up with the same relationships that these laws show. They basically do the same thing for the most part, but they are quite distinct, and we're going to take a look at them. The Biot Savart law relates magnetic fields to their source currents, which is really what Ampere's law does as well, but Ampere's law is doing it from a slightly different perspective, and it states that for any closed loop path, which we will uncover, the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability of the space times the electric current enclosed in the loop. So that's a mouthful. And we're going to see that really both of them are relating magnetic field to current. And that's what's really important about each of these. They also relate the magnetic field to the position around the current carrying wire. So let's take a look at just the conceptual idea of where we're starting from. So we already established using the first right-hand rule that if I have a moving charged particle or a current passing through a permanent magnetic field or a magnetic field that's produced from something other than that particular moving charge, the moving charge will experience a force under specific circumstances. And I'm not going to get into reviewing all that in this video, but we shifted focus then and we asked, why does that happen? Why is it that only a moving charge or a current experiences a magnetic force from an external magnetic field to itself? And so we did some investigations in the lab, and what we found is that when you have a current carrying wire, a magnetic field forms around that wire. So this current is the source of that magnetic field. And we use the second right-hand rule where you place your thumb pointing in the direction of the current and pretend you're going to grip the wire with your thumb pointing, in this case, up to the right. And what is going to happen is we're going to see a magnetic field form around the wire this is a kind of a crude drawing, but it's basically like this, right? Now, a more helpful or analytical approach to drawing this might be to show that on this side of the page, or on this side of the wire, the magnetic field is coming out of the page, and on this side, it's going into the page. So that's just a way of showing this drawing on the left in a more concise way, and it's much clearer. So the whole idea is that when I have a current, that leads to having a magnetic field. So if you readdress the question, why does a moving charged particle experience a magnetic field or a magnetic force as a result of a magnetic field that's not created by itself or not its own magnetic field? You might start to think, well, okay, if this is true here, when I have a moving charge, then I have magnetic field. It makes sense that this magnetic field, from its independently from its own self, right, from this moving electric field, will interact with that other magnetic field. All right. So, in other words, in a pictorial form, okay, I'm going to use two different colors here to really illustrate what I mean. This red magnetic field that I'm drawing right now, that's pointing into the plane of the screen, okay, that's a magnetic field from some outside source. Okay, let's just say it's a permanent magnet. And I take an electron, well actually let's make it a proton, and I shoot it into the magnetic field like this. Well, if we use the first right-hand rule, we know that the field is pointing into the plane of the screen. The velocity is pointing to the left, and so that leaves the force pointing straight down. All right. So the red magnetic field is due to itself, right? It's just due to whatever permanent charge there is. But now what I'm going to do is I'm going to draw a yellow magnetic field that is due to the moving charge. So what I'm going to do in essence is say that as the charge moves, and I'm going to ignore the curvature for right now, I'm going to just say that as this charge moves to the left, and I could even make this more explicit and change this just to a wire, for example, okay, with a current moving to the left just to make it clearer. And using the yellow now, I'm going to show the blue magnetic field. If you put your thumb in the direction of the current towards the left, then the blue magnetic field will be like this and like this on the other side. And the result of those two fields interacting will cause there to be a force, to be some sort of rotation. So that's the qualitative reason why. Now, what we're going to do is look more mathematically, and okay, how are we going to actually relate B and I? We know their direct relationship from the lab, but what constants relate them to each other, and so forth. Let's take a look. Alright, so if we have a long segment of wire here, and we want to figure out what is the magnetic field at this point, which we could call Z for lack of a better letter. We know that this wire here, so let's say the current's pointing up, there's a charge all distributed throughout this wire. And so all aspects of it, if we wanted to think in terms of calculus, let's try to make a little differential piece of this wire over here, that over the total length of the wire, I'm going to call this little current segment DL. Alright, and what I'm going to say is that from that tiny little infinitely small amount of current length, there's a distance of R to this point where we're trying to figure out the strength of the magnetic field. This distance across here is A, and then we're going to call this distance Y. Alright, now let's pause for a second. From last week, when we did a lab using the magnetic field sensors, what we came up with was a function for the magnetic field that was equal to mu naught over 4 pi times Q times V sine theta over R squared. Alright, now this is already a simplified version from the version that would be mu naught over 4 pi times QV cross R over R cubed. You may remember that cubic relationship. This shows the cross product here, which is where the sine theta comes from, and we've simplified it out. So I'm going to go ahead and say that what we are mostly looking at right now is we want to be able to use this for, because this represents for every tiny little piece of charge or part of the current moving at some velocity, you will have a magnetic field at some point from that charge. And we're going to need to use this as a baseline for identifying a few different things in the equation. Now that's for a single charge, and we are dealing with current, so let's adapt that slightly. Alright, so move this up a little bit. We're going to adapt that, so we are going to write, let's see, mu naught over 4 pi, which is all the constant, alright, times I times L. I times L, remember we had QV cross B. This is IL, okay, cross R over R cubed, but I'm going to simplify that to IL sine theta over R squared. So this is how to find the magnetic field for a current carrying wire. Now if you're dealing with a very small piece of L, then you've got to use a differential form of that. So if we write this in a differential form, we would write dB is equal to mu naught over 4 pi times I dl sine theta over r squared. So that would allow us to find, if we took the tiny little piece, so I'm going to just draw here that little piece of wire with a specific current. The current through here is constant, right? That value is I. And this little piece of it is dl, right? And let's just say the point is perhaps right here. Well, that's some distance r away, and this angle right here is theta. And we're trying to write what is the magnetic field at this point due to this small little piece dl of the current. And that would give us dB. And then of course, if we were able to integrate this, we would be able to find the total amount of magnetic field at a particular point. So let's go ahead and try to do that problem. Alright, so basically what we're going to be doing in this is taking this current, which we're going to say is running up the page. We're going to draw this horizontal axis here just to make things a little bit easier. Here's the point in question, which we'll label Z. Alright. Let's just pick this random starting point over here that we are going to call the tiny little piece of dy. Okay. We're going to call this distance over here y. And you can see we're trying to create some sort of right triangle thing over here. This distance we're going to call a, and this we're going to call r. Okay. Now, let's just say first, what's the direction of this magnetic field at point Z? So use your second right-hand rule, and you see that it's into the page. Alright. Now, what we're going to do conceptually is each little dy segment is going to have some effect on the field at point Z. So I'm going to add up all of these little dy segments with an integral. Okay, the differential variable here is dy. But you can see that theta is going to be changing as well, right? There's going to be this angle change in the triangle. And the r length is also going to change. So we've really got a whole bunch of things changing, and that's why we want to figure out what is it that we are going to use as our variable of integration, and then what things are staying constant. Well, a should be constant, right? That's not going to change. So what I'm going to do here is I'm going to put all these things in terms of y just to make them a little bit easier to use. So the first thing I'm going to write is an expression for r, and in terms of y and a, I'm going to put it's the square root of y squared plus a squared. Just a simple Pythagorean equation there. I then can also say that the sine of the angle is equal to, and we'll talk about which angle that is in a second, so here's your little clue, is equal to a over square root of y squared plus a squared. So it's this angle right here. And that is going to be changing as the triangle changes size. So we've got opposite over hypotenuse. Alright, great. Next what we're going to do is we're going to put everything into the differential equation, I mean not differential equation, a differential form of the statement. So dB is equal to the constant mu naught, the permeability of free space, over 4 pi times I times dy times sine theta over r squared. So that's just the generic equation that I'm using that says the amount of magnetic field at point Z due to that particular small little piece of dy. Now I'm going to substitute in some of the expressions that I've already used. Alright, so the first thing is I'm going to substitute the sine theta expression, and I'm going to substitute in the r expression. So that will come out with dB is equal to our constant mu naught over 4 pi times I dy. Now here's my first substitution, a over the square root of y squared plus a squared over y squared plus a squared. And remember, that was the square root of y squared plus a squared, but that's all squared because I'm substituting that in for r. Okay, so let's just do a little simplification here. Switch of colors. So next up on the simplification schedule will be this. Let's see, so that would be y squared plus a squared times y squared plus a squared to the 1/2. Alright. Now you probably can already see a nice little simplification that we can do. So I'm going to scoot this all up and switch our colors again. So dB is equal to mu naught over 4 pi times I dya over y squared plus a squared to the 3/2. Alright. Okay, good. So we've got it in a form now that we can actually start to do some integration. So basically what we're saying here is that's an expression that shows, a differential expression that shows the amount of magnetic field due to that small little place of the wire. Okay, so now when we write the integral, when I integrate this side, obviously I'm going to get B at the end of that, because that's what I want, which is the total magnetic field. And then this side, when I integrate, I can go ahead and pull out some constants, and then I'll put some variables, some limits in. So mu naught over 4 pi is for sure constant. I is constant because it's a constant current, and A is constant as well. So that removes a lot there. And we're going to integrate from, or let's write the expression in here. What's left is dy over y squared plus a squared to the 3/2. And if this is an infinitely long wire, I'm going to go from where y is equal to negative infinity all the way up to y is equal to infinity. Okay, now this is an improper integration with infinite limits, and it's a challenging integral to actually integrate. So I'm going to show you the solution to this, and right now it's going to be sort of magic, but you can always prove these on your own, as you know. The solution's actually going to be kind of simplistic looking, at least. And if you want to, you can go onto your integral calculator online, and they show all the steps, and it's actually very helpful. So we have this mu naught over 4 pi here, the I and the A, and the solution to this is 2 over a squared. Alright? So what that's going to do here is it's going to simplify. So let me scoot this up a little bit. So it's getting a bit messy. That's going to simplify the 2 out and one of the A's out. So I'm going to be left with B is equal to mu naught over 2 pi times I over A. Now mu naught over 2 pi, of course, is a constant. I is your current, and A is the distance from the wire to that particular point. Now the magic that happened in the integration, in integrating something with infinite limits, you have probably talked about that in your calculus class, and if you haven't, don't panic about that. You'd be able to show this purely with skipping that portion, and that's 100% fine. What we're going to do next here is I'm going to post some practice examples that you can take a look at, just for a few different variations. But let's do this exact same problem that was really brutal. If you have a headache now, I understand. But let's take a look at it from Ampere's law's perspective, and you'll see how much easier this is. So I'm going to do a quick side-by-side comparison of Gauss's law to Ampere's law. So I'm going to just list this as G and A. So G for Gauss, A for Ampere. Obviously, Gauss's law is trying to find the strength of an electric field. Ampere's law is trying to find the strength of a magnetic field. Both are used when you have some sort of symmetry, right? Because the whole point of having symmetry is that you would have the same value of magnetic or electric field at any point along some surface or loop some distance away from the enclosed charge or magnetic dipole. This Gauss's law uses closed surfaces, and Ampere's law uses closed loops. Alright, the charge enclosed over permittivity of free space, which we've reviewed again recently, that's enclosed charge, remember it's not the total charge necessarily, is equal to the surface integral of the E of electric field times the dot product of the surface vector. Alright, and that's a closed surface integral. Now, what Ampere's law is going to show us, I'm going to scoot this up, have some space, based on the description on the first page, which you can go back and read now and see what it all means. Now, the permeability of free space times I is going to be equal to this path integral times B dot dl. So you can see how similar they are. This has the vacuum permittivity, vacuum permeability. Here we have current, charge, here we have current. Strength of electric field, strength of magnetic field. This is the surface differential, the path differential. And so what we're going to do here is use the law, Ampere's law, to do that same problem that we just did, and you're going to see it's so much easier than using the Biot Savart law. So we're going to look at the situation from above. So instead of drawing the picture like this again, with that distance A, I'm going to draw it from above. I'm going to say the current is moving into the page, and then I want to find the magnetic field at this point here, B. Alright, now I know if I use my second right-hand rule that the magnetic field is pointing this direction, so it's tangent at that specific point. So I'm going to start with Ampere's law. Mu naught I is equal to path integral B dot dl. Now I'm being lazy and not putting the vector notation above. Okay. Now we can see that if we sum all of these tiny little dl values, now is this Amperian loop that we call it, this circle we've drawn here, that's not an actual thing, right? It's a location in space. It's this useful tool that we've drawn. And essentially what I'm going to do is I'm going to break up extremely tiny little pieces of this and call them little dl pieces. And the whole idea is that B will always be parallel to every little dl piece along the way. And because all B vectors and dl vectors are exactly the same direction at every point, that's going to be able to help me here with this dot product. So basically there's 0 degrees between the dl and the B vectors. Okay, So let's actually do the integration here, which is not that hard. A lot easier than what we were doing before. So we'll leave these two things here on the side. We're going to pull the b out of here. Okay. Now we know that once we've made our way all around the loop, we should have made the circumference of a circle. So the total path integral there is going to be equal to 2 pi r. Now if I solve for b, which is what I'm trying to find in the first place, by dividing by 2 pi r, what I can see is that b is equal to mu naught over 2 pi r times I, or mu naught over 2 pi times I over r. And that's the same result from the Biot Savart. Now, this really only works when you have a symmetrical situation, or at least that's where it's easier to use. Otherwise, it becomes very complicated, and we don't want to have to use it for that. We'd rather use the brute force method of the Biot Savart law. Okay, we're going to look at just one more thing here, just like we used to do, where we look at, okay, well, what does the electric field look like inside the material, and then how does that function look as we get to the radius and then beyond it. So here I'm going to draw a wire. We're looking into the wire here. Okay, and so let's just say we draw an Amperian loop at this radius from the very center, which we'll call little r. The big radius of the wire is r, and I'm going to define current density with this letter J, and that's the amount of current per cross-sectional area. And we want to find the value of B at the distance little r from the center of the wire. So we're going to make just a side assumption here. We're going to say that mu naught, the vacuum permeability, is the same as the material of this wire, which it's not necessarily, but we could change that number to fit, just like a dielectric constant idea. So the first step in any problem using Ampere's law is to draw the Amperian loop, which we've defined right here. It's at that radius little r. Okay. Now, one thing else I'm going to do here is write that I is equal to JA, and this is a uniform charge density. Okay, I'm going to write my equation out. Mu naught I, Ampere's law, is equal to path integral B dot dl. All right. Now I'm going to substitute the JA in here. Okay. So on this side over here, well, let's expand this one more time. So we'd write mu naught times J times pi r squared, because that is the area. All right, and then that's all equal to this. Okay. Now we know that the angle is 0, which is why I got rid of the dot product, and the cosine of that is just 1. So that's great. All right. Now at this point, we're going to integrate, right, along that path. And the left-hand side is left like this. And the right-hand side, if we integrate that, pulling out b, is we get again 2 pi r. So b times 2 pi r. Okay. So if I solve for b there, you'll see that that will factor out, and b will be equal to mu naught over jr, or b naught times jr over 2. So if you graphed the strength of the magnetic field at any distance from the center of the wire up to the actual radius of the wire, you would get this relationship. And we already just found the other relationship, which was as you pass the boundary of the wire. So the graph in its entirety would look like this, with this being the radius of the actual wire. Alright, so hopefully that you'll be able to go through that again. You can work some other example problems and try to verify what's happening. The one last thing that I would add, just hopefully as a help, would be what if we had, say, two wires, one with a current up and one with a current down, and and they have the same current, and I drew my Amperian loop around both of them like this. Alright, well, you can see that what's going to end up happening here is that the net current through the Amperian loop is going to become 0. So this mu naught times I, that side of the equation, is just going to become mu naught times 0, right? So then that would be that 0 is equal to path integral B dl. So then the magnetic field, basically what it's saying, is 0 on the outside of those two wires. And this is what a coaxial cable often is made of. It has a current running up the center, let's say, and then the outside cylinder of the wire is also carrying a current in the opposite direction down. And then what happens is that coaxial cable cancels out any magnetic field from either portion of the wire, and on the outside we have 0 amount of current. Now if you were to draw your Amperian loop just around the inside wire at that distance r, again you would just get the equation mu naught over 2 pi times I over r. So it would be the same as what we had found from before. So good luck doing some practice problems, and try to extrapolate different views of this, and we're going to take a look at a solenoid next.